Alright, hello everyone. In this video, I'm going to be going over Bohr's theory of the hydrogen atom. Um, in this video, we're going to go over some calculations, just some like conceptual stuff, and then we'll get into one that goes back into doing the light equations because I have a feeling that might be on the test. If not, it's always good practice. So we're going to do one of those at the very end. Yeah. Alright, so this is Bohr's theory of the hydrogen atom. So with Bohr's theory of the hydrogen atom, we are going to be calculating the amount of energy emitted or the amount of energy absorbed in order to move an electron up or down energy levels, right? So we'll get into that in just a little bit, but the equation for this reaction is that the change in energy is equal to negative RH, which is negative 2.18 times 10 to the negative 18 joules. I'm going to actually check and make sure that that is right. Yep, okay. Just wanted to check because the two 18s being there were kind of suspicious to me, but so we're all good there. And it is multiplied by 1 over n final squared, and that is minus 1 over n initial squared. I use not initial as sometimes often, just an I, right? I want to say that's what he did in his. Yeah, so he put an I there. So you can do it either way. I always use not. Again, like I have a lot of physics background, so for me, not is what makes the most sense, right? But it means the same thing as I. This basically means initial, and that also means initial as well. So now let's look at this conceptually, right? So we have this atom here. Let's pretend that this is a circle, guys. It's really hard to draw circles on my little drawing pad, so please, you know what, make fun of me. Actually, you guys, I highly encourage you to make fun of me for this absolutely horrible drawing. But let's pretend that this is a Bohr hydrogen atom, or just a Bohr atom, right? So you guys may have learned that a Bohr's model, you have, oh my god. You have your rings, these are your energy levels, and you have electrons that might look something like this, right? So you have those two, and you have these going around. So this is the same Bohr's model that we're dealing with here, right? It's the same exact one. But in this scenario, let's say we're moving this electron and we're moving it down here. Maybe we're moving this electron up. We're going to be calculating how much energy that takes or how much energy is emitted when something like that happens, right? So here's a little picture of an electron. It can either go up a whole bunch of energy levels or it can go down energy levels, right? So with this, it requires energy to move up in energy levels. So if an electron wants to move up in energy levels, meaning it goes from, let's say that this is energy level 2 up to energy level 3, 4, 5, right? So let's say this electron wants to move all the way up from energy level 3 to energy level 2. That is going to require energy. It takes a lot of energy for an electron to do something like that. Oh, I don't know. Depends on what you think a lot of energy is. But it requires energy to do that, right? But if the electron wants to move down to the first energy level from the second, energy is going to be released, right? So this is actually how we view light, right? So a lot of the reason why, you're doing... This is going to be a horrible drawing. Oh my god, please don't turn out bad. This could go really bad right now. Oh my god. Okay, guys, that's a flame. And you have a stick of, let's say, copper, right? This has copper on it. You guys might have done this in high school, but let's pretend I know what color copper turns, and I should know it. I'm pretty sure it usually turns like a blue or green flame. But let's say that you get a green flame out of that, right? So the reason why it turns green is because you're putting in energy, and that's going to be moving this electron around, right? But when the electron moves down in energy, it releases energy, right? So it's going to be releasing energy, which is oftentimes light, right? So that's just like a conceptual thing that you guys can think about. horrible drawing. I'm not an artist. But how I like to help myself remember this is I think of it like a hill, right? So if you're going up a hill, you're gonna be sad. You're gonna be just like this dude. He's sad. He has to go up a hill. It's gonna require energy. After it, he's gonna be exhausted, right? So you have to have an input of energy. So plus delta E. So plus change in energy, right? You have to add. But when you're going down the hill, it requires like no effort. If you just let your body go, you will roll down the hill. I'm sure you loved doing that as a kid. That was one of my favorite things to do, is roll down a hill, get completely dirty, and then your parents yell at you, right? That was my favorite thing ever. So it requires absolutely no energy, and you're actually, I guess releasing energy in a way. But that's how I think of it, right? So it requires a lot of energy to go up in level, and then to go down in level, you're releasing energy. So that's how I like to think of it. But there's like the conceptual stuff, right? So let's get into a conceptual problem. Alright, here it is. Which requires the highest input of energy? I do highly encourage you guys to pause the video and try this out yourself. But in just a second here, I'm going to go over it. So feel free to pause now and try it yourself. Okay, so for A, let's look at A first. We're asked which requires the highest input of energy. So that means that our delta E is going to be positive. So we're going to be going up the hill. So we need to go from a low energy level to a high energy level. So let's look at the first one. Okay, so we're going from 1 to 2. So we're going from a lower energy level to a higher. So I'm going to star this one, because if the rest of them are going from high to low, then that might be the answer. So I'm going to star that one because that one could be right. We'll come back to it later, right? So now let's look at this next one. We're going from 5 to 3. When we go from 5 to 3, we're going from a high energy level to a low energy level. That means that this delta H, or the delta E, my apologies, the change in energy is going to be negative. So we're releasing energy, and that's not what we're looking for. So we're going to say, no, you're not the right answer, because you're going to be releasing energy. Again, not what we're looking for. Next question. We are going from 2 to 4. 2 to 4. Okay, so I'm going to also start this one because we're going from a low energy to a high energy. So that means that we're going to have an input of energy, right? Because we're going from lower to higher. So this delta H would be positive, so I'm going to star that one. This one is greater than this one, so I can cross this one out now, because this is only moving from 1 energy level, and this is moving from 2, so this is going to require more energy. Okay, now let's think about this one. We're going from 5 to 2. Same thing with B. We're going from a higher energy level to a lower energy level, meaning that we're going to have to release energy. So we're going to say, no, you're not the answer. So that gives us C as our final answer. All right, moving on to the next question. It says, calculate the change in energy when an electron moves from energy level 5 to energy level 1. Was the energy absorbed or released? All right, so same thing as I had on the first slide. We're going to be using this equation. Change in energy is equal to negative RH. 1, this is n squared final minus 1 over n squared initial. And we know that RH is equal to negative 2.18 times 10 to the 18 joules. Alright, so let's get to solving this. So, we have the change in energy, which is what we're looking for, so we're going to keep that variable there. Oh my, what happened to my E? Change in energy is going to be equal to negative 2.18 times 10 to the negative 8. Nope, not negative 18. I'm going to check that real quick, make sure I haven't been writing it down wrong. Oh my gosh, it is to the negative 18. Why did I just know? So this is 10 to the negative 18. Oh, I had that right before. What the heck? Huh, okay, I just was moving too quickly, I guess. And then we are going to multiply that by 1 over. I'm going to just write out the 1 over, because I'm going to now think about this, right? What would be our energy level final, right? So we're going from 5 to 1. So that means our final is going to be 1 squared. And our initial, because we're moving from, so we're going from 5 to 1. So our initial is going to be 5. All right, so change in energy. I'm just going to simplify this a bit. So we have 2.18 times 10 to the negative 18. And we're going to multiply that by 1 over 1 and minus 1 over 225. And I'm going to do that out in my calculator now, which I don't have handy, so I'm going to use my phone calculator, and hopefully everything turns out fine. Do 1 over 25. Okay. Alright, I'm going to have to use, like... How am I going to do this calculation without my TI Inspire? Alright, let's figure this out. 2.18 e to the negative 18. Sorry, this might take a second for me here because I'm trying to do this a very odd way. Hopefully Google saves me here and gives me an answer. Alright, I'm going to hope that this answer is correct. Feel free to let me know if this is wrong, because I literally use Google for this. Since we don't have sig figs here, I'm going to go to 3 sig figs. I think that's what he had said to do, times 10 to the negative 18. So I'm going to assume that seems about right. It might be to the 19 possibly. Let's see if I can do this out actually. 2.18 times... Because phone calculators don't really allow you to do that, I guess. Oh, maybe they do. 10 to the negative 18? No. Okay, that just doesn't work. So I'm going to hope that that's the right answer. If not, you have the calculation there, and feel free to do it on your own. I wish I did have my actual calculator with me right now, but it's unfortunately all the way in my kitchen, and I don't feel like getting it. So we're going to have to deal with that. Okay, so moving on to the next question. Nope, not that one. We want this one. Alright, so this is the harder one, that's similar to what we did in class. So it says, in the Bohr model of the hydrogen atom, an electron moves from, I'm going to write this out here, moves from 6 to 2. I'm going to write that this is the energy level. What is the wavelength? So that's what we're looking for, is wavelength, in nanometers of the light emitted. Okay. So what I'm thinking right now is that I'm probably going to go from the change in energy to doing the energy is equal to h times frequency equation, and then I think I'm going to go and do the C is equal to, what is it, lambda, I think it's lambda F, check my sheet here, yeah, lambda, he uses mu again. In the last video I explained that I use frequency just because that makes the most sense to me. But yeah, so those are the equations that I'm thinking I'm going to do. If it doesn't work out, then we'll try something else. But that's the process that I'm thinking of doing right now. Okay, so we're going to do change in energy is equal to negative 2.18 times 10 to the negative 18 joules. There should be a negative in front of that. And then 1 over the final, which would be 2 squared, minus 1 over 6 squared. Oh. Okay, so change in energy is equal to negative... Actually, I'll make that positive now so we don't have to deal with that later. 2.18 times 10 to the negative 18. And then it's going to be 1 over 4 minus 1 over 36. And then the change in energy. Alright, maybe I can photomath this and I'll end up a little bit better. I'll feel a little bit more confident about my answer if I use photomath, I think. Do I not have Photomath downloaded on my phone? That would be... Okay, I do. I was gonna say, like, that was a huge clutch in, like, Algebra 1 in middle school. Like, I have to have that downloaded. Okay. How old are you? These apps are crazy. It's so embarrassing to write down that I'm 20 and I'm using Photomath. Sorry, I have to re-download this app in order to check this answer. You guys have probably already have this done on your calculator, but we'll take a brief pause. We can't recognize your problem, yeah, because it's in handwriting. 2.18 times 10 to the, how do I do an exponent on this? Negative 18 times 1 over 4 minus 1 over 36, and we get 4.84. Again, this is using a non-calculator method. I guess Photomath is technically a calculator, but it's not as efficient as an actual calculator. Joules. Okay, so I'm gonna underline this answer because I know I'm gonna use it in the next question. So the next one I'm gonna do E, change in E, I believe is what it is. Oh well, not. We'll just do E is equal to HF. And just to look back, H is equal to. Let me write down my energy first. Oh, this should be negative energy, correct? Oh, no, it's not negative. Okay. 4.84 times 10 to the negative 19 is equal to H, which is 6.626, I believe. 6.626 times 10 to the negative 34th. Yep. Times 10 to the negative 34th frequency. And let's divide those two. I'm really regretting not having my calculator on me. This is too funny. Okay, 4.84 times 10 to the negative 19 divided by 6.626 times 10 to the negative 34. Oh, I wrote X in there instead of, that's funny. I wrote X instead of times and it was like solving for X. This is why you need to have your calculator ready at all times. Okay, so this is the answer that I got. I got F is equal to 7.31 times 10 to the 14th. And this will be in hertz or 1 over seconds. All right, and again, like, these answers might be slightly off because I'm using Photomath and not like a real calculator. But if your procedures are the same and you're getting different answers and you're making sure that your exponents are correct, then yeah, you're fine. Okay, so the next one I'm going to do is C is equal to lambda F. And we're solving for lambda, so we're finally getting what we need to. So C is equal to 3 times 10 to the 8th, which is equal to lambda times that frequency that we just got, 10 to the 14th hertz, or 1 over seconds. And just as a reminder, this is in meters per second, so we are going to have to do another conversion after that, but that is okay. We will get through it. Times 10 to the 8th, and I'm going to divide that by our frequency, which was 31 times 10 to the 14th. And for lambda, I got 4.10 times 10 to the negative 7. And now from there, we're going to turn this into nanometers. So we're going to do one last calculation. We're going to do 4.10 times 10 to the negative 7 meters divided by 1 times, we want nanometers, so there's 1 times 10 to the 9 nanometers in 1 meter. Again, that is definitely something that you're going to want to write down. If you have your 3x5 index card, that will be really helpful. So our answer is 410 nanometers. That's our answer there. So I didn't have to do a calculator with this, so just as a reminder, when you're doing sig figs, you can just look at the exponents. So if I'm doing 10, 10 to the 7th times 10 to the 9th, all I have to do is negative 7 plus 9, and that will give me 2. So it's times 10 to the 2nd, and all I did is I moved this over 2 times. But again, you can put this in your calculator, you'll get the same answer. But that's just kind of like the mental math way of doing it. But it's safer to do it with your calculator, trust me, 100%. I trust my calculator more than anything. But there is the final answer, and thank you all for watching. Sorry for the chaos with the photo math, but if you guys have any questions, feel free to reach out, and good luck.